Today, let's talk about...
When we talk about bioceramic materials, we have to talk about bioactive glass ceramics. These raw materials still have a lot of interest among the researchers, even when the first bioactive glasses were created back in 1969 by Larry Hench. And it is due to the great versatility that their properties provide them.
Something that both bioglasses and bioglass ceramics share is their reactivity with biological systems, which is pretty useful for regenerative medicine as these materials aid the body to heal faster. It is because of a variety of factors like the liberation of therapeutic ions, which is especially helpful in the recovery process of, for example, a certain number of patients with different diseases like cancer or diabetes, whose system response will be lower than a healthy person. Furthermore, they have other extra properties that make them interesting materials for the design of biomedical devices like a hip implant, where the BGCs can create a coating over the surface of the metallic compounds as the femoral stem. Some studies have shown that the creation of this interface between the hard tissue and the metallic stem can form a better union when the crystalline phase in the BGC contains apatite, at the same time that this coating can be produced with mesoporosity to allow the vascular activity, and also with control over the volume fraction of the crystalline phase. It can mimic better the properties of the bone, but could help to reduce the damage into the tissue due to the bone and device mechanical differences. Other things that are currently being researched and developed are new products for cancer treatment. Some compositions of bioglass can produce a ferrite phase when they get partially crystallized. These phases are magnetic field sensitive, which make them vibrate and heat up, and the cancerous cells are more sensitive than the healthy ones to the temperature rise. So one of the ideas is the production of BGCs nanoparticles with this property. Accommodate them into the problematic area, activate them through a magnetic field and eliminate the cancerous cells and let their bioactivity aid to help the surrounding healthy tissue. The new scientific ideas about how to take even more advantage of BGCs are just related to their capability to help in the recovery process. The current work is focused on how to manipulate the liberation rate of the ions from the BGCs to optimize their contribution to heal the tissue. But to achieve this new goal, as it is also for manipulate the rest of its properties, it is necessary to control the size, shape and volume of the crystalline phase. And then is when the real challenge comes.
The main problem is that it doesn't matter which synthesis route we use, there is always going to be something that's going to produce an uncontrollable and spontaneous crystallization, like the fast crystallizing in salt gel due to the high content of hydroxy groups or residual carbon or nitrogen, or in melt quenching that is produced by the low Poynter rates, ion exchange with water, or even the light elements volatilization. So we don't have to completely control the rate, or not yet. Fortunately, there is one possibility of solution that is even being applied to many other science fields:
the simulation. The idea is use characterizing techniques such as differential scanning calorimetry, Fourier transformed infrared spectroscopy, and nuclear magnetic resonance to analyze these materials and their evolution through the treatments, to understand things like heat temperature change, identify the formed phases, and know the elements' coordination and spatial distribution. And then, with all this information, accomplish a computational modeling that could allow us to create schedules for the chemical and heat treatments to get the most optimal material, not just for each different application, but also for each patient's necessities.